soon, I guess. So while Greg is setting up his talk, I just wanted to give a very quick introduction. So Greg did his doctoral and I think part of his postdoctoral work in the mathematical and technical sciences in Warsaw, Poland, and then he's come on. So I don't know where he was before he started his position at MCG, but he's been the director of the statistics department and the bioinformatics core at MCG for the past few years. So he's got several awards, including the NSF Young Investigator Award and many other awards. And here he can tell us about his work on stochastic models and how he's using that for system global analysis. So join me in welcoming Greg.
I am very sorry for the delay. The parking arrangements are always mysterious. And I am not very good at, I guess, moving in an environment when I am not sure, what is the proper parking space and what is it not. So it just took me a couple of minutes to figure it out. Okay, so you've basically just shaved about 15 minutes of my talk. So that's good, right? I will try to not to be overly excessive therefore. This presentation is basically a recycle of a portion of the talk that I gave at the workshop about 6 weeks ago in Banff, in Canada. And this kind of relates to some of the work that myself and several other colleagues of mine, mostly from the University of Wisconsin and then from Concordia University right now, have been working on and off for a couple of years. These methods that I will be talking about are really related to stochastic modeling of biochemical dynamics. But it turns out that they have some connections with bioinformatics, and I will basically at least attempt to sketch out what those connections could be. Okay? Now, do you have some kind of, I guess, pointer or a clicker or something I can just use a mouse. I can use the stick, but I prefer not to because then I can hit something. So I would like to move this presentation. Okay, so here's the story. I will briefly talk about chemical kinetics in general and the stochastic version of chemical kinetics in particular, because that's what I will be interested in. Then I will briefly talk about how this relates to some models that people have put together in a variety of contexts, not always necessarily related to biology. Some of these have been originally devised for population dynamics model, in particular for analyzing stochastic models for epidemics. But then I will sort of try to go back to the things that I'm really interested in, which is developing or devising methods for analyzing genetic networks, and I will try to introduce in this context something which we call a multinomial model for the reaction cone, and then I will introduce some kind of likelihood-based inference for that particular structure. That inference and the overall statistical analysis is really dependent upon one key idea, which is called the algebraic statistical map. And then, whatever kind of statistician you are, you can basically pick up your favorite theory and you can apply it. If you're a Bayesian, you can basically take a Bayesian model and you can very, very nicely build up this very similar type of inferential procedure that I have built. I am not going to be talking about this too much because it gets a bit too technical, and this is not the main point. I am not sure how many of you guys really are interested in theoretical statistics. But at the very basic level, I at least would like to introduce some of these concepts and explain why do we care about, why do I care about them, and why does NSF care about them. Okay. So the reaction networks, the general sort of classical chemistry. I understand that your Bioinformatics Institute is in the Department of Biochemistry, so that's perhaps appropriate. Sort of classical chemical kinetics notation. And it goes like this. I have a molecule of a species A, a chemical species, and a molecule of the species B, and they combine together to create a molecule of species C at some rate. Okay, that is called K. Now, in general, what I would like to do, I would like to consider a network of these kinds of interactions that I will call a biochemical network, and that network will have a number of chemical species, A1 through AN, and those chemical species will be related to each other by the set of chemical reactions. Okay, so this is sort of the underlying model that I'm looking at. This is exactly the sort of standard classical chemistry setup. Curious. Okay, well, so I guess I just have to be patient. So, there is several different ways in which you could try to describe classical chemical theory. In sort of basic chemistry 101 that many of you have taken, you would think about chemical reactions as following in a very, very large volume of molecules some kind of deterministic dynamical system, typically describable by the ordinary differential equation, following one of the standard assumptions about the kinetic rates, for instance, something which is called the law of mass action. I will talk about it a little bit more later on. But in the settings of molecular biology, in particular in the biochemical systems in which we are interested in looking at the possibly poorly understood chemical structure, meaning that some of the equations might not be exactly right, or looking at small number of molecules, meaning that the times until the reactions would actually not be negligible. The time until the reaction would itself be a random variable, and it would take a certain amount of time for these molecules to react together in some closed volume. In such settings, it is often convenient to develop a sort of alternative approach to biochemical reaction models, which is based on the Markov process. Okay? So in this setting, what I am doing basically, I am developing this relatively simple probabilistic or stochastic structure in which I am saying I have a relatively small number of molecules. If these molecules get in close proximity to each other, and this is sort of a baby picture for this, then they will react. There will be a chemical reaction. But because there is relatively few of them and they're floating around with these diffusive motions, then basically for a long period of time, there will be no reaction. The mathematical description of such type of system is very often given by something which is called continuous time discrete state-space Markov process. And here is basically the sort of generic description of such a process. Okay, so at time t, I am looking at xt, which is the vector of molecules that are describing the system that I'm interested in. And this system evolves in the following way. It looks at what happened right before t. So at t, it looks at t minus. This is the state of the system right before. And then, at this time t, the reaction k happens. So therefore, the change in the state of the system at this point is given by whatever was before, xt minus, plus the difference between the number of molecules that were created as the result of the kth reaction and the number of molecules that were consumed in the kth reaction. Okay? So this is my move in the discrete state space. I am basically moving my molecules, I'm counting molecules, so this is a counting process. Basically means that the description of the process is the counts of all the chemical species that I care about at time t, and then if the kth reaction happens, then this state changes by annihilating the number of new prime molecules that were part of the reaction k, and the creation of new prime molecules as a product of reaction k, and then annihilation of new k reactions as